Okay, welcome back to CS225, and we are going to be today moving on to, instead of trees as an abstract idea, more concrete trees. So, let's talk a little bit about finding things in trees. So, here is an example tree, right? How would we do find, say, n? Let's think about this. If we want to find n in the tree, how long is the running time, do you think, of any algorithm? Log n? How am I going to do log n? I like n. I'd like it to be log n. Okay, so we have an algorithm if node equals n return else search right, search left, which I agree is a correct algorithm, but the running time of that algorithm is going to be n. Oh, we're assuming it's a binary search tree. This is just a tree, right? It's a binary tree, right? We have not made a binary search tree. I don't know what that is yet. So I think that the way I have to do this, I potentially have to search every node, right? So it's certainly not log n. If it's sorted, it's log n. I'm not sure I agree with that. This doesn't look sorted. So I think the best I can do in this is n, right? Since if I do find z, I have to go through the whole tree, right? That z doesn't exist, but the only way I can write an algorithm, because the algorithm doesn't know the contents of the tree, it could know structural properties, it knows it's a binary tree, but as I said, that's the only property we have is that it's a binary tree. So to find something, it's going to take order n. So this is no better than what we saw in a list, right? Finding a element that contains something in a list, we could do order n. So maybe trees aren't any good. Well, that's not going to be the answer. But, huh. Let's think for a moment. We're going to probably want to restructure this tree, but also we want to talk now about an abstract data type. Now, with trees, there are lots of things you can do, and a general tree is very general. But there's one abstract data type that we're going to spend about half of the remaining semester talking about, which is the dictionary. The dictionary abstract data type is a super useful data type. It's so useful that some modern languages have it built in. And it organizes data into keys and values, as in, well, the words and the definitions in a dictionary, right? So if I know the word, I can look up the definition in the dictionary. On the other hand, knowing the definition doesn't help me find the word. So it is a key value pair. And it shows up everywhere, right? So the name comes from dictionaries, but, well, we could have the course number to the lecture and lab schedule. So is it like a map? A map is a concrete implementation of a dictionary in some languages. Right. It maps the idea of from the keys to the values. On a graph, we'll talk about from a node to the incident edges, which are right. We're reviewing some of the graph material. The edges that are connected to that node. In an airline system, we have flight number to arrival information. And in fact, the entire internet can be thought of as a dictionary, which maps URLs to HTML pages, right? So this thing's everywhere. What are all the operations we want? And we're going to do this Can there be multiple keys? Well, a dictionary has multiple words. Can multiple keys point to the same definition? Absolutely. Could the same key appear multiple times? Not in our particular description of the dictionary. That is to say, every key is unique. So that's a good question. So, I'm going to work through the abstract interface here along with functional. So first we want to have find, right? That it's what we already said we did. We look up words in a dictionary. So the most basic thing we have is find. So find key and return value. Right? The very most basic operation. Okay. We could do this concretely in a couple of ways. I'm going to use the function find, but in many C++ implementations, what you'll see is square brackets, right? And in fact, actually, in many languages that have dictionaries built in by default, the square brackets operator, which we've been thinking of as array access, is really dictionary access. So, let's try and think, what do we need here? Well, we want our dictionary to be templated, right? So we're going to have template, type name, in a sense, an array is a kind of dictionary. I agree. In a lot of ways, an array is a dictionary. It's not quite what we're doing. A dynamically sized array, I would say, would be a dictionary. The thing with an array is all of the indexes need to be contiguous, right? That if we have index 1 and index 57, we have to have index 2, 3, 4, 5, 6 on up to 57. And that is something an array requires that a dictionary does not. So type name, right? And I'm going to have the type name of the key, right? So we're going to do find const ref key. Right? Is there a way to order a dictionary, like if we had a custom way to order keys? This is an interesting question. The dictionary ADT does not require it to be ordered, but some of the implementations we choose are going to produce ordered dictionaries. So you can think of a dictionary as ordered or unordered, and we haven't really got to how that's going to come up. But it's an interesting thing to ask. Is the contents of a dictionary in order or not? But what's find going to return? I've given you a big hint. Well, so we're templatized under two different data types. We're going to return a value. So there's a possible concrete implementation. Okay, so find, I think, is the most primitive operation, though it's not very useful without actually having a way to put things in. So we better have insert. So insert to dictionary. We're going to have void insert const ref seems good to me. Key const ref v value. Okay. Should find be a const function? That's a very interesting question that I'm not going to answer right now. And it really depends on how you've implemented find and what you do when you do not find something. And that's a design decision that I'm not touching right today. Remove is going to be remove is going to be something like void remove const ref k key. Again, what is it doing? It here is always returning something. So what do I do if I can't find? Well, I would... What do you mean insert at the back? It inserts in the dictionary. We access things in the dictionary by key. If I built my dictionary with a list, pushback seems fine. If I built my dictionary with something else, perhaps I'm going to do something else. The concept of inserting at the front or the back doesn't matter because the way I get things out of the dictionary is with find. So how the dictionary is storing this data, we haven't talked yet. Right? We could imagine that if I just keep it in an unordered list, I go through the whole list, I find it, I can return it, I can just insert. Again, we haven't talked about an implementation. We can't talk about how the keys are sorted. We can't talk about these things because we don't have anything to do. So it should have constructors, destructors, all of those things. I would argue that the way I've written find is a very common way to write find. Would we want a size? We don't need that from the point of view of the basic type. So there's one last thing we want, which is traversal. So using iterators. So we have a way to get all the keys out with a traversal. And I claim that's really all we need, right? Would we like other things? I think size is a fine thing to have. I think that check to see if a key exists is a fine thing to have, which is different than find. And we could talk about that maybe find should return something else, like perhaps an iterator to pointing at the element it found, at which point we can do it. But I think this is the basic idea. Okay? So we want to do find, we want to do insert, and we want to do remove, and we want to be able to go through the data structure and finally initialize it. So we could implement this dictionary, and I could tell you right now, your lab is go write a dictionary using a linked list, right? And you could do it. It would not be efficient. Let's see, what would running time of find be on our linked list? I think it would be order n, right? Insert could be constant time. Remove would be order n, because I have to find the element to remove. And traversal is order n. So we would have, if implemented with a linked list, it's very straightforward, and we know how to do it, right? It would not take you long to do it. But we're talking about trees, so maybe we want something better than order n. So let's talk about a binary search tree, which is something we're going to use to implement a dictionary data structure. So, okay. So here is a binary search tree. What's true about it? Our binary search tree is going to be ordered. Could you implement a dictionary with an array? Sure. It's going to be ordered such that everything to the left we want smaller and the right we want larger. That's not what we have here, is it? There's no order. This was our binary tree. So right now with our binary tree, we do nothing better than we did with a list. But what can we do with a binary search tree? Or a binary search tree, or a BST, is a binary tree such that either it's empty, or right? And root of TL key less than R, root of TR key greater than R, and TL and TR are BSTs. So binary search tree. So is this a binary search tree? If I look at it, it looks like it is, right? 38 is the root. Everything to the left of 38 is less than. Everything to the right of 38 is greater than. Can we implement binary search tree using... Can we implement a dictionary using a binary search tree if we don't have a comparison operator? No, because we can't have a binary search tree if we don't have a comparison operator. If we don't have at least less than, we cannot, or greater than, it's not a binary search tree, because a binary search tree is defined by the ordering of the values. I mean, 13 is less than 38, and 51 is greater than 38. That does seem a problem. We would do something. I'm not going to worry about it right now. Right now, with a binary search tree, we cannot handle all data types. We can only handle data types that are orderable. If the child of 25 was greater than 38, would it still be a binary search tree? No. No, it would not. What's the advantage of this over a sorted list and array? We're going to get there. But so there's our structure. So, okay. So here is our binary search tree. It has a type, it's looking like the dictionary, right? It is a binary constructor. It has insert that takes a key and a value. It has remove. Our remove version is going to return the value given a key. Find returns a value. Tree iterator doesn't change things. And our tree looks like what? Every tree node has a left, a right, a key, and a value, and has a constructor, and it starts with a head. Why do we want key as a reference? Some can be references, some can be not. What is the key and value in a BST? Well, what are you putting in? In this BST, which is how we're going to talk about them most of the time, we are showing the keys, because that's what matters, right? A BST is ordered by keys, and the value, who cares? The value's in a box. It's somewhere in a box, and you can get it out. So this is actually worth spending a tiny bit of time about, because from now on, we're going to be almost always talking about a key value pair. That we're going to have keys, and then somewhere there'll be a value. Well, what's the value? We don't care. So when we draw our data structures, we're going to just draw the keys. Because if I put a bunch of values in this node, it would just be harder to read. And it doesn't affect our algorithm at all, right? All of our algorithms on our binary search tree, which we're using as a dictionary, are only going to care about the keys. The values are just things you hand to somebody. Somebody gave you a value, you put it in a box. When you're done, you give the value back. Okay. So let's try and write some of these functions. Let's see. Let's work on find. How do we find in a binary search tree? Can we get constant find times in a binary search tree? I don't think so. I don't think we're quite to log n yet. I would like us to be. It would be great if this got us to log n. But let me show you a binary search tree. Let's see. Here is my binary search tree. Right, that's still a binary search tree. So a binary search tree is not quite perfect, but it's a really good place to start. So how does find work? So we're going to start at our root, and let's say we want to do find of 25. Okay? Find of 25. So let's see. It's going to take a key, and it's going to return something. Well, I think we probably want a helper function here. So find is going to, let's see, it's going to do find So I'm intentionally using auto here to hide what find's helper function is going to do for us. So, okay. So we have our helper function. Our helper function is taking, in the other order, it's taking a root and a key. Auto gets its type from the return from what it's initialized. So we're taking our root and our key, and now let's start trying to actually write this function. So if, what's our base case? How about, what can happen here? What could go wrong? What is our base case going to look like? let's see, if root is null. Yeah, because we need to have if root is null. If root equals null, right? Or null pointer. What do? We do return it. Seems like the thing to do, right? Root. So now I know what the type of my function needs to be, right? It needs to be a tree node pointer. Our helper function is going to return the pointer. It is. Okay. So how about a more useful case? What else can we have? We have if root's not null, we can do stuff like root key equals key, right? Yeah. Root is a reference to a pointer to a tree node. So if root's key equals key, well, this is kind of our other base case, right? Because writing on slides is inconvenient. Okay. So kind of our second base case is we've found our node. Okay. So now what's our recursive form? If root arrows key is greater than key, let's see, if the root is greater than the key, that means the key is smaller, so we go left, right? Return find root arrows left, comma, key. Else find root arrows right, comma, key. Okay. So if the root is larger, we go left. If the root is smaller, we go right. Okay. So what do? We have to get a little bit of pieces here. We got to say, arrows temp, arrows value. But we now need to deal with if temp, do that, else return null. Or we're returning a value, so we will return a v constructed by default. Okay. Now, could we decide other things? We could instead return an iterator. What's the point of the find without the underscore? That's the public find, right? As the user of my BST dictionary, I don't know what root is. Root or head, none of this makes any sense to me, right? That's not a publicly available thing. I can't call find on root. Root is hidden inside the BST, and this outer find uses the root internally, right? Our public interface, our private interface, right? So when we're recursive, we almost always, okay, auto will automatically type the, at this point we are returning a v, right? We return a default value, right? We're templated, so this constructs a default object of the type v, and we return a value. Well, then we would be returning a pointer if we wanted to be able to return null, and we don't really want to return a pointer. Auto x5 doesn't quite work because 5 is an incomplete type. When do you need a helper function and when not? Well, recursively, usually we want a helper function because the external doesn't know. I could, instead of saying this, I could say tree node pointer. What does if temp means? Well, if temp is null, then this is false. If it's not null, it's true. If we cannot find the node in the tree, we will return the default value. Yes, auto knows the type returned by the find helper function. What is v? This is calling on the type v, right? A default constructor. You can always use iteration instead of recursion. In a tree, because of the way in general heights are controlled, recursive solutions tend to be clean and easier to write. In other cases, it's less clear. So, okay. So find just searches through the tree and finds the correct node with the key. That is correct. So, if we do our find of 25, wow, this is the worst pen ever at the moment. Our find of 25, what do? We call our helper function. We call 38. 25 is less than 38. We go down. We call 13. 13 is... Sorry. 25 is less than 38, yes. Then 25 is more than 38. We go watch. We compare. And we're going to... The helper function is going to return this pointer. Okay. If we don't find it... So if we do find of, say, 89. 89 is larger than 38. We're now going to be calling on this one, and then this one, and then this one, and we're done. Okay. So find is pretty easy. What is our running time of find? So is the worst case the height of the tree? Yeah. So our running time of find, the most precise we can give is order h, where h is height. Height is kind of internal. If I don't have access to height, what's the tightest bound I can give for the running time of find. So if I can't say height, and I agree height is the most precise thing I can say, yeah, unfortunately, as cool as a BST is, the best we can get is n, right? Because my BST could be a list. So BSTs are great. So how do we now deal with the case of 59? Well, let's talk about the next thing we want to do. We want to do insert. So let's try and figure out how we do insert. How do we do insert? Well, I'm going to propose first 2 changes to our helper function. Let's go back and look at this helper function. Well, this is const. I don't really like that being const. We probably want a const version, but I'm going to write one that's not const. And instead of returning a pointer, I'm going to return a reference to a pointer. Right? So I've made one tiny change. If I did find on this tree, find using my internal helper here, right? And I did find, and we'll use the number that somebody was asking. What about 59? So 59 is not in the tree. What's going to happen? What is find's helper going to return? Let's see. Find is going to do find of 38. 59 is greater than 38, so we go up. Well, I agree the value of what gets returned, it's going to be a reference to null. And there are a lot of nulls here. So which null is it going to return? Yeah. So it's going to go 59 is greater than 38. It's greater than 51. It's less than 84. And it is less than 66. And it's going to return that pointer that is null. Right? So this is find of 59. Is going to return a reference to that pointer. Well, if I want to insert 59, where do I put it? Yeah. So, right of 51. Right of 51 already has 84. So left of 66 is exactly where 59 has to go, right? Yeah. So how do I write insert? Insert with the assumption that all keys are unique will be and we can write this in a couple ways. So I'm going to write this the confusing way first, I think. Find of root key, and we are missing a little bit here, value, the value should be an %v that way. New tree node inconsistency with our naming scheme is the answer. What do you think of that? Insert the helper function takes the root as the first parameter and the key as the second parameter. Public insert doesn't take root as a parameter because public doesn't know about root. Is find useful on a key that has not been inserted? Not particularly as we defined it. Should we delete the previous node in its place? So we could decide how we want our dictionary to work. And there are a lot of different choices here. That we could make it work such that it was wrong if you inserted the same key twice, much like the standard C++ array is wrong if I access out of bounds and it's just terrible, or we could make it do something else. Why would I leak memory? It seems like there's a memory leak if you did it like this. What's the memory leak? Find is going to return, so if we are doing insert root, right, and this gets called with the usual wrapper, so we're going to insert 27 and some data. So 27, find is going to return what? I'm not removing a tree node. If we insert a key that already exists, this will be corrupting. We're trying to insert 27. If it exists, it'll be left, so find is going to return this pointer. And what am I doing? I'm updating that pointer to point to a new node that is 27. So find is become this pointer, and it can be on the left side, and I allocate a new node here, and I'm there. If there was a node at that location, you replaced it without deleting it, I would have a leak. If I did it to, say, 51, so if I did insert of 51 on this data structure with this thing, I would actually lose all of the subtree of 51, wouldn't I? So this version of insert only makes sense if you have already guaranteed that the key does not exist in the tree. Before we called the insert helper function, we could do something to verify that it does not exist. Yep, we could check if find was null, and if it was not null, we would just do nothing. We could, the key for 51 is 51. Yes. I'm only writing the keys because the values don't matter, right? The values are just a box. Somewhere there's a V here. But I don't care. The only thing I'm going to write in these trees is the key of the node. Because algorithmically, the only thing we ever look at is the key. It's the only thing that's interesting from the algorithm's point of view. So I could change this code to make it not corrupt, or I could wrap this code on the outside. I could change this code to, if the key already exists, I could replace it or update it. Those things are all fine changes you could imagine. But I wanted to show writing it this way because this shows something that's a little bit unusual and often bothers students. That this function is on the left-hand side of an assignment. Why do we take root as a reference to a pointer? Here you'll note we didn't need it, did we? That I could have written this as a recursive function, right? But I simplified my life. If I took it as a reference to a pointer, I could write this whole function recursively, right? By taking all of the code from find and copying it in to insert. At which point I would need a reference. So here I don't actually need it to be a reference to a pointer. That is a good point. Okay. So insert's pretty easy. If we had const at the end, we'd not be able to assign a new tree node. Right. If there was const at the end of insert, it wouldn't work. If there is const here, we couldn't return the tree node pointer by reference. Is using a helper function any slower than writing the code in the original function? No, effectively. Yeah, remove is pretty easy, but remove I'm going to wait until Wednesday for, because remove is going to take a little bit more. Don't I need to check it that the node is null? No, I just like, as I said, that when we think about an array, right, if we insert into an array index that is not there, then that is an error. An error, right? So if I allocate an array and then I try to insert into past the original, find, what is find returning? Let's walk through. Find does recursively start at the root. We're going to try insert of, let's try 29. I don't know if that's one I did before. So we call find helper here. Find helper says the root is not null. 29 is not equal to 38. 29 is less than 38, and it calls find on this pointer. Find recurses again. It says the root is not null. 29 is not equal to 13. We are going to recurse. 29 is greater than 13, so we call recursive find on that. Find recurses again, says 25 is not null. 25 is less than 29, so we recurse on this. The root is not null. 37 is not equal to 29. 37 is greater than 29, and we return this. And insert returns, or find returns this pointer. We change this pointer to be 29. So what happens? Let's look at the broken case. If we did insert of, let's say, 51, because this is going to go badly. So insert of 51 says, well, we start on root. 51 is greater than 38. We have found 51, and it's going to return this pointer. What are we going to do? We are going to change that pointer to now point at a new node, 51. Oops. We have lost, weak memory, and lost all of this. So, it's an error. Just as I say, like if you have a vector and you try to read the value at 1,000 plus the end of the vector, it's going to just crash on you, right? You're going to get a seg fault. And this is the same thing. Now, could we choose a different method? We could update this code to look at find. If find is null, we do this. If find is not null, we update value. Right? And it all depends on how you define your data structure. The problem with updating the value is if those values are constant, I can't do it easily. And then we'll have to talk about replacement. And we'll get to that on Wednesday. We will talk on Wednesday about removal from the data structure and about how to handle these more complicated cases. So right now we know how to do find, and we know how to insert. So as long as we only add to our dictionary and we only put things in uniquely, we have a arguably better dictionary, but not that much.